Consider this word problem. Relative to the ground, what is the gravitational potential energy of a 55 kilogram person who is at the top of the Sears Tower, at a height of 443 meters above the ground? First thing we need to do is understand the word problem. One way to do that is to draw a sketch. So here's the ground. And a picture of the Sears Tower. I'll just simply draw a tower. And it has several floors on it and some windows. And it says, relative to the ground, what is the potential gravitational potential energy of a 55 kilogram person who is at the top of the tower? So we'll put this individual here at the top of the tower. And we're asked to find its gravitational potential energy. Let's look at potential energy for a moment. There are different kinds of potential energies. I'll just write them over here, potential energies. And potential is another word for stored. Potential energy means stored energy, ready to be used. Now there is chemical potential energy. Chemical potential energy. This is stored energy in a battery. So it's stored and it's just ready to be used. Of course, what's going to come out is electricity, but that electricity is generated by a chemical reaction inside. And then there is mechanical potential energy. And that's part of the spring right here, or the pen, I should say. This pen has a spring inside. And as I click on here, I'm going to give that spring some energy. It now has stored energy, waiting for it to come back out. And as I click it again, a little mechanism here will release the spring, and out comes the tip. So it's stored energy. And here's what the spring would look like inside my pen. So a spring is a form of mechanical potential energy. Well, what we are really interested in right here is gravitational potential energy. And this is a function of gravity. And we're going to use G as 9.8 meters per second squared. This is the pull of gravity on an item. This is our potential energy. We're interested in gravitational potential energy. This is the one that we're going to be using. In order to use this, we need a reference point. And the reference point is typically the ground. We're going to call this, here's the ground. And we're going to call the ground as height equals 0 at this level here. And the higher you go up, the greater the gravitational potential energy becomes. Here at this point, your gravitational potential energy is 0. You're not going to be able to fall down. But the higher you go, you have the potential to fall down. As a result, you are gaining potential energy. And the height of this tower right here is given to us 443 meters. That is the height of the tower. And the individual is sitting way up here. Hence, he has gravitational potential energy. Another way that I look at gravitational potential energy is if the item, whether it be a person or an object, has the ability to fall down, then they have gravitational potential energy. Obviously, he can easily fall down with reference to the ground. The equation we're going to use for gravitational potential energy, let's look at our equation. Here it is here, potential energy. And I put in the subscript gravity is equal to the mass times the acceleration due to gravity times its height. And the height is with respect to a reference point. I'll talk about that in a moment. So here's our equation. Potential energy is equal to the mass of the object that we're interested in this case, the mass of the individual on the top, times the acceleration due to gravity. This is the force that's pulling down. And the distance from the reference to where the object is. In this case, we call it height. Now, I spoke about distance once before. I'm going to make another comment here. Distance. There is no specific letter of the alphabet to represent distance. As far as distance goes, it has the unit of meters. All distances has a unit of meters. That's our base unit. As far as a variable from the alphabet to represent distance, we have used x. We can use y. We can use s. And in this case, we're going to use the letter h. And we've used r. There is no specific letter in the alphabet that designates distance, but they all have the unit of a meter, regardless of what's used in the equation. In this particular equation, we're going to use h. H represents height, but it's just the distance from here to there. Writing down now a list of what is given in the word problem. And write given. And we're given the mass. I know this is mass because of the unit kilogram. And we're given a distance in terms of height, 443 meters. I know that's a distance because of the unit of meters. And gravity is always working on us. And we got the focus back, just waiting for a second. And gravity is always working on us. And this is understood. Why is this individual going to fall down? Well, gravity is going to bring him down. It's simply understood. The pull of gravity. And that has a value of 9.8 meters per second squared. So we have all the units that we need in order to solve for potential energy, gravitational potential energy. I'll just shorten that to gravity. Is equal to the mass of the item, 55 kilograms, times g, times the height with respect to a reference. This reference is 0 here. So from here to the very top is 443 meters. Potential energy then is equal to, putting these numbers in the calculator, we'll come to 238,777. And the units, nothing cancels out. So we have kilograms, meters times meter, meter times a meter, and everything divided by seconds squared. Looking at the units, we know that this is a Newton times a meter. And a Newton meter has been given a special name of a joule, represented by the letter J. All energy, potential energy or kinetic energy, all energies has the unit of a joule. Now let's look at the number. And we need to reduce this to significant figures. And we have 3 and 3. These are the two measurements. So we'll reduce this to 3 significant figures. Approximately equal to 1, 2, and 3. We could write this 230. Look at that fourth one, round up. 239,000 joules. Or we can put this in scientific notation. 2.39 times 10 to the power of, decimal point is here, 1, 2, 3, 4, 5 joules. Now let's have a look here. If I were to say to you, I want to know what his potential energy is with respect to the first, or somewhere up here, the second floor. And if I were to arbitrarily say the second floor is 50 meters above the ground, therefore his potential energy with respect to the second floor is this height right here. And that height would be 443 meters, the original height, minus the 50. I can put that quick number in here. 443 minus 50, 393 meters. So his potential energy with respect to this floor here, which is 50 meters above the ground, I'd have to redo the calculation using this as height. So potential energy is with a reference. You decide where the zero reference is going to be. Typically we consider this the Earth. Here's the Earth. You want to consider the surface of the Earth as 0. Surface as 0. That's our reference point for gravitational potential energy, but it can be anywhere higher. All depends on us. Strictly a reference point. Is a reference for gravitational potential energy. And that is the term H. Equal to, the mass is a constant. Gravity is a constant. That H, well, that is with reference to the 0, which you determine as to where you want to calculate your potential energy. And with that,